Hello guys, so let's have a little look at what the specification says we have to learn for C12.1, the first lesson. First you need to be able to state the link between the periodic table and proton number. So if we go and have a little look at that, let's go to the periodic table. Basically what you need to know is that as we move across the periods, that they are ordered by their proton number or the number of protons that are in their nucleus. So you can see hydrogen has 1 proton, helium has 2, then lithium 3, beryllium 4, boron 5, carbon 6, and so on and so on. And this is what makes the periodic table so ingenious, because Mendeleev ordered these before we really even knew that there were these things called protons. He was able to order these things together. And it just so happens that if you order them in this way, in increasing proton number order, that when they line up with elements of similar reactivities being in the same group. So the link between the periodic table and proton number is that as we move across periods, the proton number increases, or they're ordered in increasing proton number. You need to be able to say where all of the following things are on the periodic table. They will assume that you know that the group 1s are called the alkali metals, the group 7s are the halogens, the group 0s or the group 8s are the noble gases. You need to know about hydrogen, and you need to know about the transition elements, okay, and where they are. So let's just have another quick recap on that. So all the group 1s, these are called the alkali metals. They are the most reactive of all the metals, and they are ordered with the most reactive metals being at the top. So being at the bottom. So lithium is the least reactive, followed by sodium, then potassium is a little bit more reactive again. We're allowed to use these in the lab: lithium, sodium, potassium. They won't allow us to use rubidium, cesium or francium because they are just simply too reactive for us to use in the school science lab. I would highly recommend watching the periodic table of videos on rubidium, cesium and francium, because you get to see exactly how reactive they are. I'll put a link to those 3 videos on the Google Classroom for you. You'll see here that hydrogen is highlighted in the group 1s. You need to know that hydrogen can appear at the top of the alkali metals, but it can also appear, as it does on your periodic tables, in the middle here, kind of not really belonging to any group at all. And that's because it is actually a non-metal, so it actually should in reality belong over here with all the other non-metals, but it does have 1 in its periodic 1 in its outermost shell. So all of the group 1s here all have 1 valence electron, or in other words 1 electron in their outermost shell, and that's why they all have similar reactivities. It says you also need to know where the halogens are. The halogens of this group here: fluorine, chlorine, bromine, iodine, astatine, and tennessine, which is, in fact, we've only made literally a couple of atoms of this. Astatine is radioactive, so you don't have to worry about astatine at all. That's never going to come up on the exam. Fluorine we can call evil fluorine because it's incredibly reactive, so they don't let us use it at all in the lab. In fact, you can't even store fluorine in a glass container because it will react with the glass. Fluorine will even react with xenon, which is an unreactive noble gas. It has a full and stable outer shell, so fluorine is ridiculously reactive. So you only really have to worry about chlorine, bromine and iodine. They're the only 3 that we have to worry about in terms of the halogens. But again, they all have 7 valence electrons because they have 7 in their outer shell, and or they all therefore react in a very, very similar way. We also need to know where the transition metals are. So the transition metals are all of these, the blue and the green ones here. So you might wonder why these ones are down the bottom here. Well, the reason why these ones are down the bottom here is because actually they should slot in between here. Can you see? If we said that they were ordered in order of increasing proton number, you can see this one, lanthanum, has 57 in protons in its nucleus. Well, you can see here that cerium has 58, praseodymium has 59, so these actually slot in here between these two. And this one, thorium, protactinium, all of these along here slot in here. Now, the only reason why they're down the bottom here is because it would make the periodic table ridiculously long. So we don't put them in there, we just put them down the bottom. But they are all transition metals. And so the thing about the transition metals is that they have what we call variable oxidation states. Now, I know that sounds a bit scary, but it just means that sometimes they give away 2 electrons from their outer shell, sometimes they give away 3, sometimes they give away 4, 5, 6, 7. Some of them sometimes give away 7, if you can believe that. And it means that each atom doesn't give away a specific number of electrons in their outer shell. They can give away multiples, which means that they can react with a whole array of other elements in different ways and in different ratios. We don't need to worry too much. The chemistry of them is actually quite complicated. You don't touch it until, at the very least, end of A level, so don't worry too much about it. All you need to know about the transition metals is that they form coloured compounds, and B, that they form variable oxidation states. You also need to be able to define valency electrons. Now, valency electrons is just a fancy pants way of saying outer shell electrons. So whenever you see valency electrons, just think outer shell electrons. It's how many electrons do they have in their outer shell. And you can use the periodic table to find that out too, because the group 1s all have 1 valency electron, or 1 electron in their outer shell. The group 2s have 2 electrons in their outer shell. Like we said, the transition metals here can have multiple amounts in their outer shell for very complicated chemistry reasons, which would just blow your hippie mind if I talked to you about it, so don't worry. The group 3s here, they have 3 in their outer shell. The group 4s, 4 valence electrons, or 4 in their outer shell. The group 5s, 5s, and so on. 6s have 6, 7s have 7s, 7 valency electrons, and the noble gases either have 2 or they have 8, but they have a full outer shell. That's what you need to know. So valency electrons just means number of electrons in their outer shell. You need to be able to state the link between group number and valency electrons. We've just gone through that. So the group 1s have 1 valency electrons, the group 2s have 2 valency electrons, and so on and so on. You need to be able to state the link between period number and number of electron shells. So if we go back to the periodic table, you can see that the periods here actually relate to the number of electron shells. Now the periods go across the periodic table. You can remember that periods go across because you can remember that periods make ladies cross. So periods go across, okay? It's a funny way to remember it. So the period 1 only has 2, hydrogen and helium. And that's because they only have 1 shell. So this one here has 1 electron in its outermost shell, or 1 electron in its only shell. And this one here, helium, has 2 electrons, which is the first shell. So that's why it has a full outer shell and it appears here. The second period, all of these have 2 electron shells, working up to neon where the electron shell is full. So 1 in the second shell, 2 in the second shell, 3, 4, 5, 6, 7, 8, a full shell. Again, this is the third period, so it's 3 shells. It means they have 2 full shells. And then the third shell, this one has 1 in the third shell, 2 in the third shell, 3 in the third shell, and so on, until this one's got 8 in the third shell. This one has 4 shells with 3 filled, 5 shells, 6 shells, Now, remember what we talked about earlier is that that's actually slotted in there. So this is all period 6, and then period 7 is the last period, which means they have 7 shells. So they're really, really, really big atoms. When you compare something like hydrogen to something like this guy here, flavorium, it would be huge because of the amount of shells that they have. Sorry, selected the wrong one there. You need to state why elements in a particular group react in a similar way. Well, that's really easy because elements only react to get a full outer shell. So what they react with and how they choose to react and in what ratios is determined by what's the easiest way for them to get a full outer shell. That's all atoms live for. So if we look at the group 1s, they all have 1 in their outer shell, even though this one's got 1 shell, 2 shells, 3 shells, 4 shells, 5, 6 and 7 shells, but they all have 1 valence electron in that outermost shell. So they're all going to react in a similar kind of way because they're all going to give away 1 electron and get rid of that extra electron so that they have a full outer shell. Same with the group 2s. These all have 2 in their outer shell. They're all going to give away 2. Now, atoms will always do the easiest option. So the metals will always give away because it's easier to, say, give away 1 than it is to gain another 7 and get a full outer shell. On the other side of the periodic table, let's look at the halogens, for example. The halogens already have 7 valence electrons. They already have 7 in their outer shell. So each one of them wants to gain 1 electron and have a full outer shell. So fluorine will take 1 electron in, which means that it will react in exactly the same way as chlorine, because chlorine will take 1 extra electron in, bromine will take 1, iodine will take 1, so that they have a full outer shell. So if we come back to here, why do they react in a similar way? Well, because they have the same number of valence electrons. So they will all form the same kind of ions, they will all react with the same kind of other atoms to form similar kind of compounds. So that's it for going through the C12.1 checklist. I hope that's broken it down a little bit. If you have any questions, please don't hesitate to put them as a group comment, a class comment, because probably if you're confused about it, everybody else is too. So you'll be doing the whole class a favour by asking the question. All right, see you next time. Bye.